So, I guess let's start with today's meeting. Uh, First, I'm going to discuss the solutions of the quiz that we did last time, and then we are going to proceed with the last topic of the third unit, that is autoencoders. Okay, so I'll share my screen. Okay, here are the few solutions for the 10 questions were there. So first question was, suppose an RNN model input training example are words. So training examples are words in the data set. That is a sequence of characters basically. How do we represent jth character in ith word? So what we are giving as input is a word, and we are training the whole uh, what we are giving as input at one time step is a character. So it's a character by character modeling. And so how do we represent jth character in the ith word? So ith word is the ith training example. So I parenthesis will show the train example number, and this angular bracket shows the value at a time step. Okay, so answer is xij. Next is, which of the following are implemented using many to one RNN models? So which of these is many to one? Image captioning is input is images, output is text. So text is not many to one, text is many to many. Then machine translation is again many to many. Input is some one language and output is another language. So these two are many to many. Text classification is classifying text into multiple categories, like okay, this text is belong to this category, this text belong to news, this some other category. So that is yes or no, class 1, class 2, up to 10 classes, like that. So text classification is many to one. And sentiment analysis is input is text and output is sentiment, positive, negative, yes, no, or some numerical value. So it's a many to one. Okay. uh, Then next is, which function is used to decide whether to update the cell state or not in the GRU. So which function decides basically? So this is always sigmoid, because which decides whether the cell state is, we are updating the cell state with the current cell state, or with the current candidate cell state, or the previous ct-1 or candidate. So that equation where we are multiplying gate with ct and 1 minus gate with uh, candidate uh, candidate cell state, candidate ct. So this equation is basically deciding. Okay, so in that equation the function we use is sigmoid, because it ranges between 0 to 1. Okay, so tan h ranges between -1 to 1, so it cannot decide. It's a negative range also is there in tan h. So correct answer is false. Tan h does not decides the whether to update the cell state or not. So sigmoid decides. Sigmoid is there in uh, gamma equation. Okay. Next is, LSTM executes much faster. No, GRUs are faster than LSTM. We have discussed this. So RNN suffers from vanishing gradient. True. Yes, RNN suffers from vanishing gradient. While training, if your gradient reaches to not a number, so you are multiplying 1.2, 1.2, 1.2 up to 10 times, and it overflows. So this is exploding gradient problem. Uh, overflowing up to not a number is a exploding gradient problem. Okay. Uh, Correct answer is exploding gradient. Next question is, which gate decides the value that is passed? So output gate decides what is passed on to activation of the next neuron. Okay. and which gates decides the updated value of the cell state in an LSTM. So two gates, update gate and forget gate, replaced by the one gate of GRU. Here we have two gates. So one is update gate and other is. So next is vector 1000. This is a one hot encoding vector. So this represents word embedding vector? No, because word embedding is mostly smaller size than the original vocabulary. Original vocabulary can have 10,000 words. So word embedding will have some 250 features. So word embedding, this is not an embedding, this is one hot encoding. So, is it so this vector represents embedding vector? No. So answer is false. Okay. Also in embedding vector you will be having uh, uh, multiple values. Some is not one. Some of these values is generally not one. It can be one, of course, but it can be 0 0.1, 0 0.2, some value. So how much that word belongs to a particular feature. So it contains the value like that. Okay. There are no zeros and ones in embedding vector. Last question is, if you have a vocabulary of 10,000 words and you perform one hot encoding for each word, so dimensions of encoding vector for each word will be 10,000, right? Because for each word you have to store all zeros and only one where that word is present. So size of vector for each word will be 10,000 exactly. So total size would be so if you are having 10,000 words, so vocabulary size is 10,000 cross 10,000. So total size would be 10,000 cross 10,000. One word is taking 10,000 let's say columns, and second word is again taking 10,000 up to 10,000 words. So all the 10,000 words are taking 10,000 columns. So vector, if you talk about vector for each word, so each word will be having 10,000 values, out of which only one is one, rest all are zeros. Okay, so the answer is true. um, Dimension of this encoding vector of each word is 10,000. Okay, so these are the solutions. Now let's switch to today's content, that is autoencoder, which is the last topic of third unit. Okay, so we have seen encoder decoder architecture. So autoencoder is nothing, it's a special case of encoder decoder architecture with two differences. So in an encoder decoder, we have seen that we have input, we have some input and it is compressed to some representation, and then it is decompressed to further the output, that is decoder part. So encoder decoder is special case where input is exactly same as the output. Secondly, the target space is same. For example, in encoder decoder, if you talk about encoder decoder, so in encoder decoder, this was you have set of words, then suppose you have some sentence in English, okay, with some words, and you want to convert it into French. So the space, uh, word space, so it consists of the alphabets from English language, it consists of alphabets from French language. So the space is different in encoder and decoder. Okay, so space in which we are having these words, that is different. Secondly, what is different is this input is different than this output. This input over here is different than this output. While in autoencoder, what happens is this is suppose this is the English sentence, and we are generating some representation of it. So the output is exactly the same as what do we want as output is in that English sentence only. So this X is exactly same as Y. So what we want to do is input is exactly same as output. So this is autoencoder, but why do we do this is we want to generate a representation of this English sentence such that we don't require this whole information, whole English sentence to store our to represent this whole English sentence. We don't want much memory. We want only compressed representation where which is having all the important information required to regenerate this English sentence. Okay, so point is we only want a smaller information, smaller representation set where we can which can be used to regenerate this original English sentence exactly. Okay, so this is the autoencoder. So this is the difference between encoder and encoder, decoder, and autoencoders. Okay, so these two are the things that are different. So we build autoencoders because we are more interested in getting a representation of the input rather than the predictive model. Okay, so it's trained to copy its input to its output. Input and output is exactly the same. Okay, so autoencoders are basically used for dimensionality reduction. Okay, over here this is the example of autoencoder. We have some input, let's say we have image, and we have compressed data. So we have compressed our information coder part, and we want to, so whenever we are applying the decoder, it should regenerate my image without the much information. This compressed data is very small, and using that very small representation we are able to regenerate our output exactly same as the input. Okay, so what we want is we want to reduce the loss where the output is equal to input, and output and input are same, and we want to reduce the loss, so difference between our y and x, that is output predicted y and actual x, should be zero, almost zero. Okay, so this is our target. So it's extremely fascinating. Deep learning is extremely fascinating in that sense because we can solve a variety of problems and almost any problem with our deep learning. Okay, how here we are solving the problem of data compression. We are compressing our data in such a way that there is no loss, there is lossless compression. Okay, so these things are not possible in machine learning. In machine learning you just create a model, you just predict whatever, predict or any other methodology, so anything. But in deep learning what is possible is you are extracting features. This feature extraction part, feature extraction or the better representation of the data, this is possible in deep learning only. Okay, so this is another so let's see the basic architecture of autoencoder. So here we have input function exactly the same as simple neural network. We have f theta 1 and g theta 1, two functions, just like a simple neural network. The only thing is number of neurons in different layers. So in input layer number of neurons would be different in hidden. So the only difference is we are reducing the number of layers as we encode, and we are improving or increasing the number of layers as we are decoding. Okay, so that is the only difference. Simple neural network. Now, uh, Consider the case where dimension of h, that is the hidden layer, is smaller than the dimension of xi. So what happens in that case? If dimension of h is smaller than xi, what will happen is some information from xi should be would be lost. Okay. So we want to store those values in h which represent the relevant information required, all the relevant information required to regenerate that xi, okay, that input. So h basically contains only important information about xi. It does not contain irrelevant information. So this is the case where we have h which is smaller than that is the size of hidden layer is smaller than the input and output layer. So in that case, basically what I'm trying to say is we are decompressing our data, we are compressing our data, and after compression we only have the relevant information out of the whole data. We don't have the whole data, we have a smaller part of that, smaller subset or representation of that data. Okay. uh, where you have hidden layer which is larger, size of dimension of hidden layer is much larger than the input. What happens in that case is, now h is again the representation of input data. So what happens in that case is, so input is exactly copied to hidden layer, and the remaining part is uh, some more part is added, because dimension of h is more than xi, so it can store all the information in xi, plus it can store some more information. So this is basically called the overcomplete autoencoder. It is not required because we have xi, and xi is already having some information, and if I am converting it into a hidden layer or hidden representation where it is storing information with xi, plus it is storing something more than required, more information which is required to regenerate xi. ठीक है, so this is called overcomplete autoencoder. Generally this is not preferred. Okay. uh, Next is a choice of activation function. So which activation function will you use if input is of binary? So can any one of you tell me what kind of input would be there? So there are three inputs. First is tanh, second is sigmoid, and third is linear activation function. So out of these three activation function, which activation function will be used in place of f while decoding? I'm talking about decoding over here. Can you think of anything out of tanh, sigmoid, and linear? Anyone? No clue why, which activation function we can use and why?
Sigmoid.
Sigmoid, right? Why?
हम यूजुअली बाइनरी प्रोबेबिलिटीज हम लोग उसी से डिटरमिन करते हैं.
Exactly. So the point is, because output would be, we want output as 0, 1, 1, 0, 1. Input was this, and we want the same output, same thing as output. So my output, if output is 0 and 1, so I'll use sigmoid. Range of sigmoid is 0 to 1, so I'll use sigmoid. Range of tanh is -1 to 1. So there's negative values also. So we'll avoid this one, and we will avoid linear as well. Okay. So again, now if we are having real valued inputs, then what will be the activation function, this f, at the time of decoding? Tanh, sigmoid, or any other that's in your mind, linear. So tanh we cannot use because its range is -1 to 1. Sigmoid we cannot use because its range is 1 to 1. So for those values which are 1.25, uh, we want a 1.25 over here. So we want a real valued activation function, which is a linear activation function, which means that we are not applying anything, we are just calculating this as it is, and in place of function it's just the value that is they have multiplied. So this value multiplied by weight plus some bias. So this whole is a linear activation function. So here we'll use linear because we don't want to reduce our values to some range. Okay, so here we will be using linear activation function. Okay,
Ma'am,
yes.
can we use ReLU here?
So what is the range of ReLU?
0 to infinity.
0 to infinity. So if my value input value is minus 1.5,
Yes, ma'am. Then it's not feasible.
right. So 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 generally we use so depends upon what kind of input you have. If you have only positive values you can use that. Okay. Okay, so next is denoising. So denoising is very interesting part. So over here, so what happens is, uh, over here, what do we do is we are corrupting our data, okay, with some additional noise. This is noise. So we are actual input was this. We are adding some noise and then we are training it, okay, and then we are and we want this xi to be as same as this. Now question arises, there is two things. If there are two things. First thing is okay, okay, this is let's say my autoencoder architecture. Okay, I'm giving x original x as input, and I want predicted y to be same as x. Okay, second case is I want I'm giving x as input. I had x as input, but I will give corrupt x having some noise. It's having some noise. Okay, then I want predicted y to be same as input. I want output to be same as this input, not the corrupted input. Okay, so in that case, okay, so if you are planning to do this and if you are planning to do this, so which one will give you more error? Here you are training on the corrupt input. You are training autoencoder on the corrupt input instead of the original input. Okay, so which model will give you more error, left one or the right one? Getting my
Corrupted data.
right. So question was when I'm training this model on the original input, and when I'm training my model on the corrupted input, which will give me more error? Definitely this will give me more error. Okay, so error would be high and here error would be low. But in real world what happens is we do this actually, we add noise to data and then we train it. Now what is the reason for doing this is that suppose I had an input image which was something like it is a learning a character which is something like this 3. Okay, this was 3. It was having some noise. Okay, okay. So what happens is if I am corrupting this input, so I am instead of learning this whole 3 letter, I will add noise over here. Then okay, so I am drawing it very poorly although. Okay, this is again 3, so this is noise over here, noise over here. So in this 3 what I am doing is this is noise and this is noise. So now instead of learning the whole letter, I am learning the sub parts. So point is, I'm learning this portion, I'm learning this portion, I'm learning this portion, I'm learning this, and so on. So instead of learning the whole letter, I'm learning some representation, some smaller subsets of three. Okay. So what is the advantage of doing that is this portion. Suppose I'm learning this portion. Okay. This portion you will see if you have nine, some letter nine. Okay, 9. So this portion is common in this 3 and 9. So this part is common in 3 and 9. Now my model is learning 3. Now my model is learning this part. So it will work for letter 3 as well as it will work for letter 9. So getting the point is, if I am learning subparts of it instead of learning the whole letter, what will happen is my model will represent most of the similar cases related to this. Okay, so this is the idea. So idea is, so if now I'm training my model on this kind of image where we have smaller representation, smaller subsets of the original images, added some with some noise over here, noise over here. So I'm learning this, basically I'm learning this, and I'm learning this. Okay, so if I'm learning this, so whenever my model encounters this, it says, okay, this is not a noise and this must be the part of some letter. Okay, so whenever my model encounters this, it says, okay, this is not the noise and this is the part of some letter. So what happens is, if I'm training on such kind of data, what it will give me is, so it will learn quickly and it will learn similar. So whenever my image is this too, so it will learn it quickly and it will say, okay, I have seen, even if my input was not having to, it will say, okay, input, even if it's not training on actual 2, but it will say, okay, it can recognize this and it will store this representation, and it will say there is something like this, there is something like this, there is something like this. Okay, something in like this in the model, and rest all is noise. Then when you regenerate your image, it will generate 2. Okay, so this is the overall idea of the adding noise. Basically what it is doing is, it is reducing the overfitting. So if you are training your model on exactly whatever is the input, this is overfitting. So this thing is basically reducing the overfitting from the data. Although the output whatever you get is y equal to x cap, so there is some error, somewhat more than the error in that case where you train the original image. So you are training on 2 3, and you are applying autoencoder, you will get some error. So this error a is basically larger than error b, uh, where you are training on corrupted input. ठीक है, you are training on corrupted input AE, and you get some error B. So A is B greater than B. So why? Because you are training on corrupted input. But this is the case in the training. What happens in the testing? During the testing means you have unseen examples. So unseen example can be having this too, and it can be having two. So in both the cases, the test error uh, a dash is less than b dash. Okay, I have written opposite, I think. Yes, over here. So this is like this and this is like that. I will erase this. Okay, so in that case, training error would be low, A is low and B is high. Okay, in this case, A will be high and B will be low. Whatever, so my goal is basically on test, it should be low. So why it is low? Because in second model, and in first model. In second model, the testing accuracy will be higher, but training accuracy will be lower. uh, okay, so what, why is it? Because this second model can train on both types of input, while first model can train on only on the actual input. Okay, so that is why testing accuracy is higher in second case, but training accuracy is higher in first case. I hope you are getting. So this is overfitting. So this second model is reducing the overfitting, because here training error was high and testing error was low. So this is overfitting in general scenarios, we know that. So this is reduced by denoising. Okay, so this is the idea behind adding some noise in the model, ठीक है, in the input image or whatever data we have. So denoising autoencoder is a one that receives the corrupted data point as input, and it is trained to predict the original uncorrupted data. And finally, when it reconstruct the good image. It reconstruct the image which is having no noise. Okay, so this is denoising. Next is sparse coding. So sparse autoencoder is nothing. So if I have a neuron, so I will say it is activated if its value is 1. So this means activated. And if its value is 0, not activated. Okay, right? We choose it like this. So in sparse coding or sparse encoders, what happens is uh, we basically set, we want that most of the neurons in this network are 0. This means the overall average is, and what is the formula for that? Formula for that is this. This means if I have 5 training examples, 1, 2, 3, 4, 5. So what I will do is, for this first neuron, I will take average for first sample, third sample, fifth, up to five data samples I was having. I will take average, and this average value should be very low, 0.005. Okay, for this the average value should be 0.006, but for this I don't want it to be low, but for most of these I want to be this to be low. Okay, 0.002. Okay, so what they are doing is only this value, this neuron was activated, rest all were 0. So what we are doing exactly? So we are basically reducing the neurons value or activation value. So we are reducing this. So in, you remember, where do we do this? Where do we do this thing? Reducing the activations so that it has no effect. So parameters have no effect. If we have some equation like v is equals to theta naught x naught plus theta 1 x1 theta 2 x2 theta 3 x3 and some activation plus bias. Okay, so if we are reducing these to 0.00 something so that they're effective negligible, so we do this thing in uh, mm, which technique we do this? Anyone remembers? We have studied this in second unit, I think. This is basically regularization. So in regularization, we reduces our value such that the effect is overall effect of those features which are irrelevant is almost negligible. We want to reduce this one and reduce this one to avoid overfitting. So in that case, we uh, uh, make them to 0.001. So we reduce these values, right? So this is regularization. So exactly that thing we are doing over in sparse encoder. We only activate those neurons which we want that, okay, this neuron is very important to me. This stores important information required to regenerate the output, which is exactly same as my input. So I want to fire only those neurons where the activation is representing a good, it's a good representation of input. Okay, and we want to reduce most of them to zeros, approximately zeros, 0 point some lower values. Okay, So this is the overall idea of sparse encoders. Now applications, it's a very fascinating field where you can do almost so many things with the autoencoders. You can generate you can compress your data, you can classify it, you can reduce the dimensionality. So basically how dimensionality is reduced, input was something and you are reducing the dimensionality such that it is very good representation of the original image. You don't require original image, you only require the representation to generate the original image. So it's really fascinating that you had 10,000 pixel image and you are reducing it to 100, and you are saying okay, this 100 is enough to regenerate those 10,000. Then this application is, suppose there is a missing part of the image, you can generate this missing part using autoencoders. So there are multiple thousands of applications where autoencoders. So information retrieval. So in information retrieval, what happens is exactly you suppose there is a query uh, in document classification, document clustering. I will tell you how. So basically this is document retrieval. So in retrieval, basically what happens is you ask a query, okay, I want to extract those sentence or those words from suppose in a how do we search in a search engine? We have a query, I want these kind of documents, this should return, this database should return. Okay, so what happens is instead of returning all those it can be done on autoencoder, can be applied both on input side as well as output side. So it can return the set of various set of documents, or it can represent only those documents which are relevant. And secondly, while it's giving a query as input, okay, so it can optimize this query. If you are giving very large query as input, so it will optimize it and it will extract, remove words like is, which are irrelevant words. It will give you important words and which can be used to retrieve those documents. Okay, then bag of words is basically this is a way to store the information in the text. Although it's not in your syllabus, it's a very natural language processing part where it suppose you are in your document there were 2000 common words, and so it will give you, okay, this word one has frequency, it's coming three times, second word is coming five times, third word is coming. So this is basically a bag of words model. So in that case retrieving basically information, retrieving information, okay, with respect to document clustering, topic modeling. So many applications are there which over here where this autoencoders is used. Here they are showing the comparing two documents. Suppose this is document 1 and this is document 2. You want to find the similarity between these two documents. Okay, so what you do is you generate the representation of this document 1, you generate again the representation of documentation 2, and you have smaller representation, you will compare these two. Okay, because it's easier to compare the smaller representation. And you assume that this representation is generating this original word and this is representing this original document, sorry. Okay, so in that case also comparing two documents and clustering of similar kind of documents, whether these two documents are similar or not, document clustering. Okay, so this is also example of autoencoder. So there are a wide variety of applications of autoencoder, so it's a very vast field. So all these things are possible in deep learning. uh, okay, feature extraction, all kind of uh, extractions, feature representation, etc. is possible with the autoencoder. Okay, so this is I have downloaded this video from YouTube. See over here, this is data denoising. So after denoising, basically what they are doing is uh, using the representation, the image that is generated is without noise. Second thing is data restoration. So this missing nose in the image, is regenerated using autoencoder. So let's watch the video from starting. So see, so what happens is basically what they have done is there is a video and they have replaced the face using the autoencoder. So what was intact was the emotions, etc. on the face, and what was changed was the features of the face. Okay, so this is dangerous also, and this is exciting also. Everything is possible. So all this stuff, if you want to read more on autoencoder in detail, so go through this YouTube link. So it's he is a IIT Madras professor, and there are very good video lectures where he's also discussing about backtracking and backpropagation and other technical things related to this autoencoder. If you want to get into much more detailed information about this is okay. So you can visit this YouTube channel. Uh, okay. So now some homework for you. There are three topics. You have to study them yourself. Okay. Bayes theorem in unit 1. You have to study it. And second thing is hyperparameter tuning. Course to fine tuning algorithm. How do we do this hyperparameter tuning? Third is attention model. So attention model is a very vast topic. No need to get into much detail about this. Only there is a YouTube link I've provided already. Just visit this link. You will find two videos for attention model. Go through them. Okay. And in future lectures we'll discuss. So you have 10 days to study these three topics. You will be getting 4 weekend days, 2 weekends basically. So you can study these three topics, not very difficult, easier. And on 17 November, that is after your Diwali holidays, we'll discuss these three in class. If you have any questions, you can ask about these three in the class. Okay. So so unit 3 is done today. Okay, so that was it. We'll start with unit 4 on Monday, and we will also find some time for discussing how to write the project report. I hope all of you are working on project, and hopefully in November end we are doing the final evaluation. So buckle up and complete your projects. And I will say for deep learning evaluation, I will give marks for a good project report. So focus on writing a very good report or research paper, whatever. If you are writing a research paper, it's exactly the same because almost all the topics are the same. Headings are the same. I will tell you the format. So I guess on Monday, I will discuss in the last of the lecture we can discuss this project report part, how to write this report. So I will say that for deep learning, write a very good report, okay, uh, along with your project, of course. But okay, so I'll tell you guidelines on Monday. Don't be absent in that class. That was it for today. Anything that was not clear about autoencoder or anything that you want to discuss? Go ahead.